Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. Let's talk about naming compounds in this video. This is one of the last video in chapter 2, and it's one of the most important concepts in chapter 2. So please make sure you pay attention and know how to name compounds. Let's take a look at the binary ionic compound first. We mentioned before that in our previous video that binary ionic compound is made up by a cation and an anion. Those are when an element loses or gains electrons, it becomes ions. And when it carries positive charges, cation, and negative charges, anion. The table 2.3 lists some common names, monoatomic ions, some common names for monoatomic ions. So for cations, it has the same name with an element you can find in the periodic table. But for anions, when it carries negative charge, it has a name of the element in the periodic table with an IDE suffix. So introduce some small tricks, small changes on the name. And most anions have only one charge. When we name a binary ionic compound, we just put these two names together. The first thing comes first, anion comes first, and then followed by anion. Cation comes first and then anion. Here's a comparison between the name of anion and the name of that in the periodic table. For example, fluoride with an IDE, but in the periodic table, we have fluorine with INE. Let's take a look at question. What are the names of KBr and Al2O3? First, when you see the chemical formula of two different species, we first need to identify what type of compound it is. For this, potassium is metal, bromine is nonmetal, so it's a binary ionic compound. The same thing applies to aluminum 2 oxygen 3. So aluminum is metal, oxygen is nonmetal. After we identify its binary ionic compound, then we can apply these naming rules. For KBr, we can name that as potassium bromide. For Al2O3, we can name it as aluminum oxide. Just literally put these two together. So, do subscripts need to be addressed when naming binary ionic compounds? For aluminum, we have 2 and 3 in subscripts. The answer is it depends. If the cation has only one type of charge, for example, potassium only has +1, aluminum only has +3, then we don't need to address the subscript, because the set of subscript will be fixed if we have fixed the charge of cation. Now, how about we have cations with different or with multiple charges? Here comes the thing that we need to identify what charge does this cation carry. So in order to do that, we need to put the Roman number in parentheses after the name of cation, and then followed by an anion's name. And this one, the Roman number, indicates the charge that carried by the cation. The table 2.4 lists some of the common ions, common cations with multiple charge. And you can see the Roman number corresponding to the charge it carries are listed here. Some of these compounds may have nicknames to indicate how many charges it can carry. So besides mastering the systematic name with Roman number, you should also know that the common name corresponding to different charges. And that's indicated by the suffix. So if the suffix is IC, like this cuprous, it means a higher charge of this cation. If it's followed by OUS, like cuprous, then it indicates a lower charge, +1. So if I summarize some of the elements here, so higher charge can mean the copper 2+, mercury 2+, and then you change it, become chromium 3+, iron 3+, and tin 4+. So it's 2, 3, and 4. If it's OUS, it means lower charge. It can be copper 1+, mercury 1+, and then 2+, and 2+. So if you only see the IC, you cannot identify whether it's +2 or +3 charge or +4 charge. You have to combine the suffix with the name to identify which charge the cation carries. But if you memorize, have a good memorization, it should not be a problem. Now take a look at the question. What is the name of CuCl2? First, we need to identify what type of this compound is. Copper, we know it has +1 and +2 charge. So it's the ionic compound because we have chlorine, which is non-metal. So it's an ionic compound, but the cation can have multiple charges. Then we need to determine what the charge this copper cation carry. Remember the important rule, a compound is charge neutral. And for chloride, it only carries -1 charge. So in order to make this compound charge neutral, in total we have 2 chloride. So that means we have -2 charge. The copper needs to have +2 to compensate that. So it's a copper with a 2+ charge. We name it copper 2 chloride. Or we can use a common name, cupric chloride, because it's a higher charge. So a lot of these cations with multiple charges are transition metals. However, there are a few exceptions, and you need to remember: zinc, silver, cadmium. So for these three, if you see compound with these three, they are not cations with multiple charges, and you need to use the previous rule, naming binary ionic compound for this for compound involving the 3 elements. Okay, so for now we only see compounds that are made of 2 different elements. Sometimes we can have polyatomic ionic compounds, excuse me, that are made of polyatomic ions. So for those, these are the ions made up by multiple atoms or elements. For this, if we treat the polyatomic ions as a group, then the naming rule is the same as naming routine binary ionic compound. You just put the name of cation and name of anion. So the name of cation anion now, instead of just mono atom, now it can be the polyatomic ions. Some of the anions here, polyatomic anions, are oxoanions, highlighted here. It refers to anions that can contain more than 1 oxygen atoms. Okay, you can see oxo, it has 2 oxygens here, oxoanions. For polyatomic cations, we only have these 2. So if you master these 2, that's fine. For oxoanions, the naming is slightly complicated because depending on how many numbers of oxygen atoms are there, we can put prefix and we can put suffix. So in total, we have 4 different combinations. I summarize it in this chart. So we can have per as prefix and ate as suffix that corresponding to the most oxygen numbers in the polyatomic anion. So let's take oxygen chlorine, for example. ClO4-. You can see it here. is perchlorate. I leave out the root of the element here in this chart. So it's perchlorate. And then once we lose one oxygen, so ClO3, then it's chlorate, and ClO2, that's chlorite, and then ClO, it's hyperchlorite. So we have a decreased number of oxygen here corresponding to this name. If we put the same set of different groups here, on the left, you will see these polyatomic ions only have -1 charge. And then if we have 4 oxygens, it corresponds to per8. If you have 3, then it's 8. As 2 is ite, and only 1, then it's hypoite. The only exceptions here is carbonate. Although it only has, the number matches 3 oxygens and ATE, but has 2 minus charge. So the charge does not match. For another set of polyatomic anions, once you have -2 or -3 charge, then the number of oxygen change. Okay, if we have 4 oxygens in the group, then we use ATE instead of per ATE. Okay, so this is, you can see here, chromate, sulfate, and phosphate. So 4 oxygens, because it has more charge, it downgraded, it has ATE ending. And here it's 3 oxygens and ITE ending. Sometimes the oxoanions will also include hydrogen here, for example, in the phosphate family. We need to address these hydrogens in the naming, address the number of hydrogens in the naming. So first you need to see if the number of oxygens are the same. So PO43 minus is phosphate, HPO42 minus, the charge changed by the number of oxygen is not changed. So this one would just say hydrogen, phosphate. If you have more hydrogen and the charge decrease further, we just identify the number of hydrogens by using the prefix. So it's dihydrogen phosphate. We will talk about the prefix in later slides. Okay, but this is indication of how many. All right, let's take a look at the question. What is the name of Na2HPO4? After you look at this question, immediately you should alert yourself there is HPO4, that is a polyatomic ion. So you need to name this compound following the polyatomic ion rules. So the name of cation and the name of anion. Sodium, HPO4, what's the name of it? Sodium hydrogen phosphate. So that is the name. Now, we've talked about many ionic compounds. Let's move on to covalent compounds. First, starting with binary covalent compounds. The naming of covalent compounds is a little bit more than naming ionic compounds because we need to identify or indicating the number of subscripts. So naming a binary covalent compound is a prefix 1, element 1, and prefix 2, element 2, ending IDE. Okay, many steps here, but literally you just need to identify how many elements are there in the binary covalent compound and its ending IDE. If the first prefix is 1, then we can leave it out. And the prefixes can be found in table 2.6. The number 1, 2, 3, 4 to 10 are the corresponding prefixes can be found here. Let's take a look at question. What is the name of SO3? If you're just following the naming rules, the first step, you can write it as how many sulfur there? 1, so it's mono. Monosulfur, 3 oxygens, trioxide. Okay, but because the first sulfur has a prefix of 1. So we don't say the mono, we just say the sulfur trioxide. This is the name of the compound. So why we don't name this compound as sulfur 6 oxide? I mean, oxygen is -2, right? So in total for charge neutral, sulfur is plus 6. Why we don't name it as sulfur 6 oxide? That's because SO3 is not an ionic compound. It's a covalent compound. So we need to follow the rules for naming covalent compound. Okay, let's take another exercise. What is the name of N2F4? So count how many nitrogen and fluorine are there. 2 and 4 corresponding to a prefix of di and tetra. So it's dinitrogen tetrafluoride. Okay, need to change the suffix. All right. A type of the covalent compound is hydrocarbons. We talked about that in the last video too. And in this scope of General Chemistry 1, we only talk about straight chain hydrocarbons. Hydrocarbons are very special than other covalent ionic compound. We only need to identify the number of carbons by a prefix as shown in table 2.7, and also identify what type of hydrocarbon is there by using the suffix. So please remember the numerical prefixes for 1 to 4 are different from before the previous slides. So if we have only 1 carbon, we call it methane, not monothane, okay? I summarize the naming rules for alkane, alkene, and alkyne. You can determine what type of the hydrocarbons from the formula by counting how many hydrogens and how many carbons are there. Okay, so it's a prefix plus ane, ene, or yne. Sometimes, because alkene and alkyne have double and triple bonds, sometimes we need to indicate the position of a double or triple bond. So that we need to put just the numerical number starting counting from the close by terminal of carbon and counting from on which carbon we now have a double or triple bond. Let's take a look at example. What is the name of the following compound indicating the position of the double bond? Let's take a look at this. First, we need to pick the carbon backbone. So it's 1 carbon from the terminal, 1, 2, 3, 4, 5, 6, 7 carbons. Okay, now we know the prefix is hepta, right? From the 7 carbon back chain, we can see from on which carbon we start to see the double bond. If you come from the left, 1, 2, 3, 4, 5, from the 5th carbon, we see the double bond. While if you come from the right, it's 1, 2. The 2nd carbon, we see the double bond. So we pick the counting from the closer by terminal, in this case, from the right. So it's 1 and 2. The 2nd carbon, we have the double bond, so we call it 2-heptane. It's ENE. Okay. Sometimes we provide another line diagram to show it. It's the same thing. So these 2 molecules are the same thing. Yeah. Besides covalent compound and ionic compound, sometimes there are special type of compounds that we need to name. For example, hydrated compounds. Literally from the name, hydrated compounds means this compound contains water, right? It's a compound with a dot and with N water behind it. N is an integer. For example, here on the right is a powder. It's a solid powder of cupric sulfate. And on the left, we have the same compound with 5 water attached to each molecule of cupric sulfate. Again, here it's not in solution. You cannot find any liquid here, but you can see the color changed, indicating the compound formula changed. Okay, it's a special chemical bond connecting these two together. So for naming the hydrated compounds, we need to indicate the number of water molecules by using a prefix. So for these compounds, we need to write the name of the ionic compound and then prefix and hydrate as a suffix, indicating its hydrated compounds. The prefixes are the same one we used for naming covalent compounds. Remember, only the prefixes used for hydrocarbons are different. All the others are the same. And here, in this case, if there's only one water here, we keep the prefix mono here. We don't leave them out. Okay, we need to keep that. Let's take a look at an example. What is the name of CuSO4.2 water? So first, we need to write the correct name of the ionic compound. The sulfate, the polyatomic ion, has 2 negative charge. In order to make this part charge neutral, the copper needs to have 2 plus charge. So you can write the systematic name, copper 2 sulfate, and then we have 2 water, so it's dihydrate. That's the name of this hydrated compound. You can also say it's cupric sulfate dihydrate. Both of them are correct. Finally, I want to talk about acids. Acids are compounds that provide hydrogen ions in a solution. Solution means in a liquid phase, everything is homogeneously mixtured, or the solution itself. So it's a little bit ambiguous when you say acid, whether you mean a compound or you mean a solution or acid solution. So if you follow a strict rule, it should mean a solution, because if it's just compound, it follows the naming rules of covalent compounds, right? Okay. So when we have acids, we also have different types of acids. So first one is the binary acids, or it's in a solution. The naming rule is we put hydro here, and then the second name of the element, and then ending it with IC suffix, and then adding the word of acid. For example, what is the name of HCl in aqueous solution and H2S aqueous solution? Following these rules, for HCl is hydrochloric acid. For H2S, it's hydrosulfuric acid. So here are the names. Also, we don't need to address the subscript because it's fixed once you have these two combined with each other. Okay. What is the name of HCl and H2S? Please pay attention. We don't have the aqueous solution here. And in this case, I indicate that as a compound. So first, identify what type of compound it is. Hydrogen, nonmetal, chlorine, nonmetal, binary covalent compound. Hydrogen, nonmetal, sulfur, nonmetal, binary covalent compound. So the naming rule is we put the name and indicate the suffix. However, for these two acids, sometimes, as I said, it is tricky and is ambiguous in determining these names. So if we just compound, we can say that as hydrogen chloride. We don't put the mono there, say hydrogen monochloride. We don't do that. You can just say hydrogen chloride and hydrogen sulfide. So these are correct names. It's just like nicknames, like water is never been called dihydrogen monoxide. So when things come to acid, it's a little bit tricky. Please pay attention to that. Yeah. When you see this naming in the exam, I would suggest you to use the naming rules of the acid here as a solution to indicate what you see. Another type of acid is oxo acid, okay, in a solution. When you say the oxo, you should know that there are many oxygens there, and it is including the oxo anions in the compound. So the naming rule is different. We put the name of oxo anions and then change the suffix to IC or OUS and then put acid there. Okay. The ATE will be changed to IC and ITE will be changed to OUS. If you still remember the IC and OUS, these two are suffixes we use to indicate cations with multiple charge. And ATE corresponding to the oxoanion with more oxygen. So once convert that to acid, it corresponding to the suffix with higher charge. Okay, let's take a look at the example. What is the name of H2SO4 aqueous solution? Okay, according to the naming rules, SO4 is sulfate, ATE, because it has 4 oxygens here. ATE need to be changed to IC, so it's sulfuric acid. In the oxo acid situation, we don't need to say hydro or indicate any hydrogen. We just need to change the suffix of the oxo anion. So another example, what is the name of HN2O2 aqueous solution? So NO2 minus is nitrite, IATE ending. Now we need to change the ITE to, sorry, the NO2 is the ITE ending. We need to change that to OUS. So it's nitrous acid. All right. This is everything to know about naming compounds. There are so many information here, so please make sure you read the corresponding chapters on the book and read this, watch these videos carefully. Good luck in doing all the homework and see you next time.